Hello, ladies and gentlemen, and welcome to Mr. Saucedo's YouTube videos. Today we're going to be talking about how to solve combined gas law problems. So we already talked about Boyle's law, Charles' law, and Gay-Lussac's law. When you combine all of these laws together, so that's Boyle's law, that's Charles' law, that's Gay-Lussac's law, you get the combined gas law. So this is the equation that you actually need to remember. P1 times V1 over T1 equals P2 times V2 over T2. What do the ones mean? The ones are just your initial conditions. What was your starting pressure, your starting volume, and your starting temperature? All the twos are your final conditions. What was your final pressure, your final volume, and your final temperature? So the way I remember this is please vomit over the toilet, PV over T. Okay, it's a good life lesson, first of all. And then it's also a great way of remembering this very simple equation. Okay, so what do we need to remember? Whenever we're doing gas law stuff, remember, especially with Charles' law and Gay-Lussac's law, we said that you have to have your temperature in Kelvin no matter what. Why? You can't divide by zero. In Celsius, zero is a very common temperature. Also, if something is constant, like for example, in this example here, let's say that it only mentions pressure and volume. Or if it said temperature is constant. If that's the case, you can ignore temperature. And now look what you have. You have Boyle's law. So first thing, don't ever divide by zero. Second thing, if it doesn't mention something or if it says it's constant, you can cross it out, and now you just have the original gas laws we were discussing before last week. And like it says, you can always simplify these things down. So finally, be aware. Sometimes it will mention standard conditions. What are standard conditions? Standard pressure is 1 atmosphere. Standard temperature, 273 degrees Kelvin or 0 degrees Celsius. But remember, we can't divide by zero, so you have to use you have to use Kelvin, not Celsius here. These are often just abbreviated as STP. So a lot of the times you'll just hear it say, oh, you have, this, container of helium at STP. What does that mean? It means that helium is pressurized at 1 atmosphere and it has a temperature of 273 degrees Kelvin or 0 degrees Celsius. And yeah, a lot of times people are like, how's that standard temperature? We're dealing with gases. And so gases are, pretty much going to be gases at any temperature for the most part that's at near 0 degrees. So just because you make it cold doesn't necessarily mean that gas is going to all of a sudden freeze or something, okay, or turn into a liquid. You probably have to get a lot lower than zero for that to happen. So when are you going to use this gas law? Anytime you're given 2 different pressures or 2 different volumes or 2 different temperatures. So the only time you use this is when you're given 2 of each of these things, or it asks you, about, a change in one of these things. So let's use an actual example. We have a sample of methane. It has a volume of 3.8 liters at 5 degrees Celsius, and it is heated to 86.0 degrees Celsius in a container at constant pressure. What will its new volume be? Here's what I always do whenever I do these problems. I always underline everything that's important. So I underline everything. I color code it too, but that's just me because I'm weird. So I underline everything in red. That is like a given. And then I underline in blue what it's asking me to find. So let's try to use P1 times V1 over T1 equals P2 times V2 over T2 to solve this. Okay. First thing I see, constant pressure. Don't even need it. Didn't even need this kind of stuff here, okay? Next thing I notice, these are in Celsius. I need to convert those to Kelvin because I can't plug these in down here unless they're in Kelvin. And then the volume. All right, so I'm given a volume and it wants me to find the new volume. So I'm looking for V2. Always, always, always remember to convert. Okay, here's what it would look like. 3.8 over 278. Why? That's what 5 degrees Celsius is in Kelvin. V2, don't know it, it's my new volume. And then divide by 86 degrees Celsius. Well, in Kelvin, that's 359. How do I solve for this? Okay, how do you solve for V2? These two things multiplied together equals 278 times V2. So what does that mean? Cross multiply, set them equal, and then divide. You get about 4.9 liters. So plug that into your calculator though, okay? Do 3.8 times 359 divided by 278 and you should get 4.9. Does it make sense? Yeah, it definitely makes sense, right? I'm heating this up. If I'm heating this up, the volume should go up, right? Like heating up a balloon. Heat up a balloon, it's going to expand. Here's like a not so nice one, but we have a sample of diborane gas. It has a pressure of 345 torr, temperature of negative 15 degrees Celsius, volume of 3.48 liters. If the conditions are changed, so the temperature is now 36 degrees Celsius, the pressure is 468 torr, what will the new volume be? Again, underline everything that's important to you. Doesn't say anything's constant here. What I'm looking for V2 again. So I can't cross anything out, but always remember convert from Celsius to Kelvin. Not only that, this gives you a negative answer. So if you didn't convert, you get a negative volume, which doesn't make any sense at all. So let's see how you would have plugged these in, or how you should plug these in. 345 torr times 3.48 liters divided by 258 equals 468 times my unknown, so that's my x, divided by 309. Okay, let's plug these in, right? What do? Cross multiply, set them equal, and then solve for V2. So plug this into your calculator. 345 times 3.48 times 309 divided by this side, 258 and 468. When you do that, you should get about 3.07 liters. Last one. The container has a pressure of 17 atmospheres. It's kept at 32 degrees Celsius. What would the pressure be at 100 degrees Celsius? So I want to know the pressure. It gives me a pressure and it gives me a temperature. What do we notice is missing from this? There's no volume mentioned, so I can ignore it. I basically just have Gay-Lussac's law here. Always, always remember to convert. So this isn't 100 degrees. This isn't 32 degrees. I need to convert those. And so what do those look like if I were to convert them? 17 atmospheres over 305 Kelvin equals, again, my unknown, divided by 373. How do I solve for this? Cross multiply, set them equal, and then solve for P2. So 17 times 373 divided by 305. What do you get? 20.8. Does it make sense? Yeah, the pressure should go up as this gets warmer. That totally makes sense. All right, so that was how to use the combined gas law. If you have any questions, let me know. But that was it.